Have you ever really stopped to think about what's going on inside the phone in your hand or the laptop on your desk? The answer is kinda mind-blowing. It's not just some clever engineering. It's a full-on miracle of applied quantum physics, happening billions of times every single second. So, let's peel back the layers and see how all this is even possible. To really get how special our digital world is, we first got to appreciate a trend that you just don't see anywhere else. Seriously, it's a rate of progress that in any other industry would sound like a complete fantasy.
I mean, think about cars. Could you imagine walking into a dealership today and expecting to buy a car that's 5 times faster and can hold 5 times as much as the model from 5 years ago for the exact same price? No way. You get laughed off the lot. It sounds absurd. And yet, in the world of computing, that kind of ridiculous improvement isn't just possible, it's pretty much what we expect.
So what gives? That's the central mystery, right? Why do our electronics get exponentially better and cheaper while pretty much everything else just kind of plods along at a normal pace? What's their secret ingredient? Well, the answer isn't a powerful engine or some complex machine with gears and levers. Nope. The answer lies in a component so small it's basically invisible. But get this, it's the most manufactured object in all of human history. The whole digital revolution, every app you use, every video you stream, every single calculation, it's all powered by this one simple idea, an electronic switch. One that we have just relentlessly perfected, shrinking it down smaller and smaller and smaller, right to the edge of the atomic scale.
It's called the transistor. And the most important thing to know about it is right there in the definition. It has no moving parts. This is absolutely crucial. A normal light switch will eventually wear out. A transistor doesn't. It can be flipped on and off billions of times a second for years, and it just keeps on working.
So what you're looking at here is the workhorse of the digital age, the MOSFET transistor. The easiest way to think of it is like a microscopic gate or a faucet. Normally, no electricity can get from the source to the drain, but when you apply just a tiny bit of voltage to that gate in the middle, boom, the gate swings open and a stream of electrons rushes through. On, off, 1, 0, that is the fundamental language of computers, all happening right there in that tiny structure. But okay, what on earth could you use to build billions of these perfect microscopic switches on a single chip? Well, the answer is found in a super common element that makes up like a quarter of the Earth's crust. Yep, it's silicon. And as our source material says, it just became the undisputed king. It wasn't the first thing people tried, not by a long shot, but it just had this unique combination of properties that made it absolutely perfect for the job. And this slide really shows you why. Here's silicon on the periodic table, and it's sitting in this really cool spot. It's not a full-on conductor like copper, which just lets electricity flow freely. And it's not an insulator like rubber, which blocks it completely. It's a semiconductor. That means we can precisely tune it. We can control exactly when it lets electricity flow and when it doesn't. So silicon basically hits the jackpot for 3 reasons. First, it comes from sand, so it's cheap and there's tons of it. Second, being a semiconductor gives us that all-important electrical control. And third, and this is the real kicker, when you expose silicon to oxygen, it naturally grows this perfect, stable, insulating layer on its surface, which is basically glass. That natural insulator is the secret sauce for building the gate that controls the whole switch. But to really, truly understand how a switch with no moving parts actually switches, we need to zoom in, like way, way in, past the microscopic all the way down to the subatomic level. And this is where things get a little weird. You know, in our everyday world, things move smoothly. But when you get down to the scale of single atoms, the rules completely change. To understand the transistor, we have to enter the strange world of quantum mechanics. This simple model of an atom is perfect for explaining the main idea. In the quantum world, an electron can't just be anywhere it wants. It can only exist in very specific energy levels. Think of them like rungs on a ladder. It can be on this rung or it can be on that rung, but it can never ever be floating in between. So here's how the switch works. In the off state, the electrons are just sitting in their low energy rungs. They're stuck. They can't move, so no current flows. But then, when we apply that tiny voltage to the gate, we give them a little push of energy. That push is just enough for an electron to make an instantaneous quantum leap to a higher energy rung. And up on that higher level, it's free to move around. And a moving electron is exactly what an electric current is. The switch is now on. And this is the key.
The jump is a discrete, predictable event. When we remove the voltage, the electron jumps right back down, releasing a specific amount of energy and turning the switch off. This isn't random. It's a precise, controllable physical phenomenon. We can make it happen on command.
Now, don't worry, you absolutely do not need to understand this equation, but it's important to see it. This is part of the rulebook for the quantum world. Physicists and engineers use this exact math to calculate where those energy levels are and to design transistors where that quantum leap is reliable, super fast, and takes almost no energy. This is how we tamed the quantum world.
Okay, so we have the quantum principle for one tiny switch. But how do we get from a single atomic leap to the powerful computer you're using right now? Well, we do it by scaling up, massively.
The journey from sand to chip is an industrial marvel. They take highly purified silicon, melt it, and grow it into a giant, flawless, single crystal. Then they slice that crystal into impossibly thin, perfectly polished wafers. Inside these super clean factories, they use a light to essentially print billions of transistors onto each wafer. Finally, they dice up the wafers into individual chips, package them up, and those become the brains inside our devices. And the scale is it's staggering. A single high-end computer chip today can have more than 50 billion transistors etched onto a surface the size of your fingernail. 50 billion. Just think about that for a second. Every single time your computer does anything, billions of these tiny quantum events are being perfectly orchestrated, controlling the leap of individual electrons from one energy state to another. And that brings us right back to our original question. The reason computers advance so blindingly fast isn't magic. It's because their fundamental component, the transistor, is based on a physical principle, not a mechanical one. By making them smaller, we can fit more on a chip, which makes them faster and makes them consume less power.
When you really boil it down, we built our entire modern civilization by learning how to control the strange, beautiful rules of quantum mechanics on an industrial scale. It really makes you wonder, as we keep pushing the boundaries of physics, what other impossible technologies are just sitting there, waiting to be unlocked?